Let's consider some of the vocabulary associated with triangles. I'm going to draw a triangle here using this program and just get a triangle here. Now the beauty of this program is that once I get this triangle drawn, I can use this arrow key and distort the triangle in any way I wish. So let's look at this now. Triangles are classified according to their angles and their sides, and sometimes these overlap. We have the acute triangle, means that all of the angles are less than 90 in the triangle. Now this one that I sketched out is obviously not acute. This angle is acute, it's less than 90 degrees. This one is less than 90 degrees, but this one is greater than 90. You can imagine a right angle coming right here, and this one is bigger, so this is not an acute triangle. I'd have to distort it down so that all of the angles are smaller than 90. And so this is an acute triangle. All angles less than 90. Got that? Acute. Here, all these angles are less than 90. This is not the only one. I could make one of them a little bit bigger. As long as I didn't get to be a right angle or an obtuse angle, then we have an acute triangle. Sometimes it's a little hard to keep it acute, but there you go. Obtuse. I've heard some teachers, not me, talk about obtuse as being, he's very obtuse. Really, that means he's not understanding, but it almost sounds like obese. Obtuse, an obtuse triangle has has one angle that is bigger than 90. So obtuse. So if I make one of the angles greater than 90, as this is, the other two angles must be acute because a poor triangle only has 180 degrees to share. And if one of them is greater than 90, the other two must be acute. But an obtuse triangle has to have an obtuse angle. Betcha you could guess what a right triangle has to be. It has to be a triangle who has one angle. Now I'm just going to eyeball this. Has to have one angle, which is a right angle. I wonder if I have guessed properly. I could probably measure that, but let's pretend that this is a right angle right now instead of wasting time. But if there's a right angle perpendicular, then it's a right triangle. So classified according to their angles, there's acute triangles, obtuse triangles, and right triangles. Got that? You can repeat this if you didn't get it. The other way triangles are classified are by focusing on their sides. Scalene means that they're all different sizes. Look, this one has one long. This is Papa Bear, medium, Mama Bear, and Baby Bear. Scalene, they're all different sizes. Equilateral has the beginning part of the word like equal, but equal and lateral means sides. So equilateral is a triangle where all the sides are equal. I'm just eyeballing this, but I hope that you get the idea. An equilateral triangle has all the sides the same. No sides the same for scalene. Equilateral, all sides the same. And isosceles, iso means the same, but isosceles is a triangle with two sides the same, two equal sides. Now, there is some confusion. If I have this is an isosceles triangle. An isosceles triangle could be really tall, it could be really short, or it could be, it could be an equilateral triangle. All equilateral triangles are isosceles because if you have three sides the same, you have to have two sides the same. Isosceles means that you have to have two sides the same. We have some theorems that we will prove about these special triangles. And one of the things we will prove is that an equilateral triangle has not only 3 equal sides, but they divvy up their angles too. There's a theorem we're going to prove that equilateral triangles are also equiangular. And equiangular triangles are also equilateral. That's extra information. Make sure you have these 6 words. Acute, all angles in the triangle are less than 90. Obtuse, one of the angles in the triangle is bigger than 90. In a right triangle, one of the angles in the triangle is right. And since a triangle only has 180 degrees to share, there can't be 2 right triangles, so there wouldn't be anything left for the third. There can't be 2 right angles because there wouldn't be any degrees left for the third angle. Classified by sides, there's scalene, equilateral, and isosceles. Now, if you're just early in the study of triangles, you might want to stop right here, but I'm going to go on because there are other things that we need to think about. We need to think about angle bisectors, perpendicular bisectors, altitudes, and medians. My favorite one is the median. When I was a child, I used to think that, well, when I was a teenager, I thought the median was the coolest. And I kept trying to get people to do experiments, and I hope that you will do it. Median, the street has a median. That's its line in the middle of the road. You're supposed to stay on the right side of the median when you drive. There are 3 medians in a triangle, and they go from a vertex to the midpoint of the opposite side. So what we need to do is to find the midpoint of the sides. I'm going to use this construction, which is the midpoint, which will automatically find the midpoint. So the midpoint of that side of the triangle, the midpoint of that side of the triangle, and the midpoint of that side of the triangle. A lot easier than measuring, isn't it? So these, I can't move these points because they have to stay in the middle of the segment. If I distort the triangle, look, the medians stay in such a way that they're, the midpoints, stay so that they're always at the middle. Now, a median goes from a midpoint. I'm going to get a segment construction here. It goes from the midpoint of a side of a triangle to the opposite vertex. There's a median. How many medians do you think a triangle has? Yep, 3. From midpoint to the vertex opposite, or we could draw it from the vertex to the midpoint. It doesn't matter. Now look at this amazing thing. The 3 medians meet in a single point, which is very odd. 2 lines can meet in a single point unless they're parallel. But for 3 lines to meet, there has to be something extra special going on. When 3 lines meet in a point, we say they are concurrent. They have a concurrent point. And that point is right the intersection of that segment and that segment. It doesn't matter. Oops, I didn't mean that. I'm going to undo that. That was not good. I'll have to edit that out. Okay, we have these medians meet in a single point. Now the thing that amazed me when I was a girl is that median where that meets is the center of gravity of the figure. I lost one of my medians. Let's see. Let's get this back. This point to this point. This point where they meet, this on this segment. Let's see, maybe I want to see intersection point. Intersection of this segment and this segment is that median. That point right there is called the centroid. That's a fancy word. Let's see if I can type that in here. That point is called a centroid. Oh no. Centroid. Centroid. Sounds like center, and really what it is it's the center of gravity for the triangle. If you make a triangle out of cardboard, it's the uniform thickness, or even out of a piece of metal, uniform thickness, and you draw the medians and you locate the midpoint, you could take a pencil and balance that triangle on that point. It's the center of gravity. Where the medians meet is the center of gravity of the figure. And if I distort this triangle, it doesn't matter whether I make it acute or obtuse or right, where the medians meet is the center of gravity of that figure. Isn't that interesting? Medians, make sure you know what a median is. Okay, I'm going to delete these points, delete that, and delete that, and delete that, and I'm going to delete these midpoints too. Delete, delete, and delete. Because we're going to go on to the angle bisectors. Now, you could probably guess what an angle bisector is. It's a line that cuts an angle in half. And since we have 3 angles, we need to make an angle bisector. Let's see if I can find the thing that makes an angle bisector. Here it is. Angle bisector. So we're going to bisect a particular angle. This point, this point, this point. There's the angle bisector for this angle down here. If I distort this triangle, make that angle bigger, that line that we've drawn in still cuts this angle in half. Let's find the angle bisector of the other angle. So I'd have to always indicate an angle by naming 3 points on the angle, and it's important that the middle point that you indicate is actually the vertex of the angle. So I have to go here, here, and here to get the angle bisector that goes through this angle. Now let's do the third one. We see we have an intersection point. I wonder if there's magic in angle bisectors. Sure enough, look at that. The angle bisectors also meet in a point, and if we distort the triangle, they always meet someplace. And what is that place? Well, this might be a little hard to believe, but I'll tell you the secret. Where they meet is the center of a circle that will perfectly fit inside of this triangle. Sometimes graphic artists have to make a logo for a company, and they need a circle that touches just the sides of a triangle. And it might be a acute or an obtuse or a right triangle, doesn't matter. But in order to make an angle by a circle that goes inside this triangle, I need to get where the angle bisectors meet, and I have to get the distance to the side. Now the distance to the side is the shortest distance to the side, and you can see the way that this is now, that the shortest distance from where these angle bisectors meet to this side is not along the angle bisector. It has to be the perpendicular distance. So I'm going to have to construct a perpendicular line through this point. I want to go through this. No, I want to go through. Oh, first I have to create that point. I need to find a point where that's between this line there. Now I can get a perpendicular line by that point to that side of the triangle. And there is my perpendicular. Now I need to locate the point where that perpendicular hits the triangle. And it's this distance from this center where the angle bisectors meet and this point where it hits on that side, that has got to be the radius of my magic circle. Let's see if I can distort this to give you some more to work on. So I'm saying that the circle that will fit exactly inside of this triangle and tangent to all three sides has the center here, and it has a radius equal to this. So let's make a circle whose center is here and whose radius point is there, and look, we get that perfect circle inside the triangle. This is where angle bisectors meet. If I distort the triangle, look, it doesn't matter. It's always going to be the circle that's inside there. So if you want to find, and this is called an inscribed circle. If you want to find that, you have to find where the angle bisectors meet, find the perpendicular distance to a side, and make a circle, and then you have it. Isn't that kind of cool? Okay. I'm going to delete some of these, and then we'll move on to some of the other things. Thanks. Bye. Can you believe it? That was a robocall interrupting our lesson. How dare they? Anyway, we're interested in getting the perfect circle that just goes around. In COVID too, can you believe it? When we're trying to do homework from home or instruction from home, we need to find the perpendicular bisector. So let's talk about perpendicular. It means that our line has to be at right angles. It has to be a right angle for it to be perpendicular. And a bisector has to two sections, has to bisect something. Well, it's not angle bisectors, we just did this, so it's got to be the perpendicular bisectors of the sides. So I'm going to come over here and I'm going to get that construction that says we can get a perpendicular bisector. Perpendicular bisector. And I bet you're already thinking, bet you these three meet, and you would be right. There's the perpendicular bisector of that side. Looks kind of strange there, but this is a right angle. And we can get the perpendicular bisector of that side and the perpendicular bisector of that side. And sure enough, they meet in a point. Isn't the universe a wonderful place? So they meet, they're concurrent. And if we distort this triangle, we see that the perpendicular bisector, oh, look at what's really weird about the perpendicular bisector. Unlike the medians and angle bisectors that stay inside the triangle, the perpendicular bisectors can meet outside of the circle. Isn't that bizarre? Let's move it back in here where it's inside. But I'm telling you, it can be outside the perpendicular bisector. Strange, isn't it? And I've said that this is going to be the center where these meet, is going to be the center of a circle that goes perfectly around the outside of our triangle. It's the center of the circumcenter. So where the center would be, it would be right here where they meet. And the radius, this time it's easier than what we had with the angle bisector because it has to go to one of the vertices. So we just have to make a circle here that goes from this center where the perpendicular bisectors meet and goes to one of the radius points. Oh, look. Oh, it automatically went through this point and this point. Oh, because where the perpendicular bisectors meet is the circumcenter of the circle. Now watch as I distort the original triangle. It's kind of amazing. Again, the artists of this world that want to make a fancy logo need to know how to go about finding a circle that'll just perfectly fit around a triangle. Isn't that interesting? So we have these things that we've done. Let's delete this. We have one more to look at, and that's the altitude. And let's just get rid of our perpendicular bisectors and just get back to our original triangle. So I'm going to come over here and I'm going to choose this line and I'm going to delete that. And there goes our circle. Because it was the intersection of those 2 points that made the center of the circle. Anything dependent upon it is deleted when we delete that. Now we're back to our distortable triangle. We have found that the angle bisectors give us the in circle, give us the center of a circle that fits inside. The perpendicular bisectors give us something that goes outside and hits all the vertices. The medians gives us a point inside, which is the centroid and the center of gravity. The altitudes give us the height of our triangle. So that I think probably in 8th grade you learned that the area of a triangle was 1/2 the base times the height. Well, in order to find the height, we have to find an altitude. So if this triangle is minding its own business and sitting on the ground here, how tall is it? Well, you can't just put a tape measure down here on the base and measure it up here. I hope you can see that if you just choose any place, that some of those lines are going to be longer than each other. When your mother wants to see how tall you are, she leans you against the wall and takes the measurement straight up the doorway or whatever to keep track of how much you've grown. So the altitude of this triangle is going to have to be on the straight and narrow, which we would call the perpendicular. So I need to go and make a perpendicular from, let's see if I can find it, perpendicular line from this point perpendicular to that point. And so the altitude here is going to be the distance from here, and I'd need another point, to where the point of this intersection. That's the altitude. And we might as well measure an angle. See if we can measure an angle. It's been so long since I've done this. Let's see if I still remember. That angle is 90 degrees because it should be, because it's a perpendicular, so that's a 90-degree angle. Now, there could be, this doesn't have to be the top of the mountain. If you were from outer space and you stood along this line, the height of the triangle would be up to this point. So we would want to find the altitude perpendicular line from this point to perpendicular to that side, and this would be the altitude if we stood on our head sort of and thought about that. This angle is also 90 degrees. So here's an altitude. The altitude doesn't contain this part that goes beyond the triangle. The altitude is from here to here. And then there's a third altitude. I wonder if the magic of the universe holds. Do you think the altitude from the third angle will be concurrent with these other two? Only in our beautiful world. Let's find the perpendicular from this point, perpendicular to that line, and lo and behold, they are concurrent as well. The altitudes are used to find the height of the triangle, and that's distorted and show you that they're always intersecting. And look, they can meet outside as well. Isn't that interesting? Altitude can be outside. That's why sometimes if you're asked, let me make another triangle here. Sometimes when you're starting to do area and of triangles, let's see, I can't even find my, been a long time since I used this. Let's make a triangle. If you're asked to find the area of an obtuse triangle and it's sitting politely on one of its shorter sides, the altitude to that side, to this side, say, would have to be outside the triangle. And I don't really think I can. Maybe I can. Let's draw a line. Or just draw a line that goes by that point to that point and goes on forever. The altitude for this vertex doesn't go inside the triangle. The altitude has to be on the outside, and it would be, we would draw a line, perpendicular line from the vertex, perpendicular to that extended side. This would be the altitude from here to here. It's like measuring the altitude of the Leaning Tower of Pisa. You wouldn't come down to the base and measure it up the angle. You would measure it straight down to the ground. And that's just the way it is. Now let's go through our terms again. Acute triangles, smaller. All the angles smaller than 90. Obtuse triangles, one of the angles is obtuse. A right triangle, one of the angles is right. There can only be one obtuse angle, and there can only be one right angle per triangle. But acute, all three have to be acute. And there are scalene triangles that have no sides the same. There are equilateral triangles that have all sides the same. And there are isosceles triangles that have at least two sides the same. We have our special constructions that have to do with triangles. Angle bisectors tell us where the incenter is. Perpendicular bisectors give us the circumcenter. Medians give us the center of gravity, and altitudes give us the height of a triangle. So later on we can find the area, which is 1/2 the base times the height. Hope you memorize all this vocabulary. Thanks. Bye.